going to talk about instrumentation, and we're going to talk about it in broad generalities. I'm not going to get specific of how every instrument is designed, but the things I want to cover are some of the things that are common to these instrumentation and things you might run into when you're trying to do calibrations on instruments or work with them. So here is a block diagram, a course diagram of a thermocouple instrument, how a thermocouple instrument works. If you recall from Richard's charts, about the highest level of voltage you could get out of a thermocouple is about 75 millivolts. So they're pretty low. So you really need a millivolt meter here to make this measurement well. So you need first a sensitive millivolt meter. I drew in here a current source for a specific reason, is that most instruments will sense open lead detection. So if your thermocouple goes bad, it tells you that it's open. But and to do that, they typically trickle a little current into the circuit. Well, we've seen that when you hook that up to a calibrator, that'll sometimes that'll mess up the calibrator's output. The calibrator can't deal with that trickle of current coming into it. So on our instruments, because we've seen this, we let you shut that off. So in some instruments, you can shut off open lead detection so that isn't influencing the output of the calibrator. You basically, if you're using a calibrator, it's a voltage source. You've got a current source driving into a voltage source that usually creates some sort of conflict. The other thing that Richard mentioned earlier as well was setting this junction, this reference junction, to 0, and often you can do that's the ice bath reference. But what modern instrumentation does is actually have a temperature sensor on here, and they measure. So this is the cold junction compensation sense here. So you measure this junction, and then you can calculate what the actual temperature is out here. But the accuracy of this measurement affects the overall accuracy of the instrument significantly. The other thing is you make the same assumption that this is isothermic. You're really measuring at one point, and is that really true? That will be consolidated over the uncertainty budget of the instrument, of course, but those are some of the things that you challenge, that are a challenge. And this is a plot from one of our instruments of the uncertainty, the plot of uncertainty versus the actual measurement temperature. And this is the type T thermocouple, so we get down to about minus 260 here and up to about 400. And of course, as you get down, way down at the low end of a thermocouple, you're starting to get almost 2 degrees of error, not 2%, 2 degrees of error, because you're down now to very low millivolts. When you're at the bottom end of a thermocouple, there's almost no signal to work with. And through the major measuring range, you're about 0.2 of a degree accuracy. And this is based on the operating range of 18 to 28 C for this particular instrument. But here's all the things that actually go into the uncertainty budget. You have millivolt gain. So as I said, it's a millivolt meter here. Well, there's some gain in that front end. There's an analog to digital converter in there, and of course it has its own gain, and it just drifts with temperature. Your offset, both of these change with temperature, so they have to be compensated and put into the uncertainty budget. How much, you don't know. Here's the cold junction compensation, and in a lot of our instruments, this is the single biggest component of the uncertainty budget, knowing what that is. Even the display resolution gets in here. When you start getting down here to these low temperatures, your display resolution is having an effect. The table interpolation, we talked about the ITS 90 tables. Well, those are spec'd at every degree. So between the degree points, when you're measuring 0.45 degrees, you're actually coming up with that as an interpolation, and there's some error in that. It's not perfect. And then the overall system TempCo, other things are changing. As I mentioned, if you hook up something like a USB port or whatever, it starts affecting your system and things move around. So The other two plots on here, though, when you're looking at instrumentation, the blue is the high temperature limits, and the gray is the low temperature limits. So if you're this particular instrument will operate from -20 to 55 C. So that's what this is. The gray is what the uncertainty at -20, and the blue is the uncertainty at 55 C. And those are all things to know when you're making a measurement. Where are you doing it? Am I standing in a freezer and trying to make a measurement, or am I doing it in some other environment where that's having an effect or not? And how does that impact the measurement, or in your case, the calibration of the instrument? Resistance-based instruments are similar. They utilize a current source, but they utilize a current source as a reference. So to measure resistance very accurately, you apply current, and then you look at the millivolt response. And so you have some of the same problems. You have millivolt gain, you have the A to D gain, the millivolt offset, the A to D offset, and the display resolution. So those are common. But where it starts to change is the next point, the current source stability. So as you're applying this current, how stable this is comes into what level of uncertainty. And of course, when you're dealing with RTD instruments, people are looking for typically lower uncertainty. Something that's not here and is not a concern is the cold junction compensation, because now you don't have the thermocouple effects. You can ignore that, which makes it much more tolerable of an instrument for changing temperatures. So with a thermocouple instrument, when you take that into a freezer or take it out into a hot, out into a hot plant, it actually takes a while for that cold junction compensation to update to the ambient temperature. Well, an RTD instrument doesn't have that problem because it's not trying to compensate for that. It doesn't have the same issue. Typically, when you're making this measurement, you're also comparing it to an internal reference resistor and how stable that is, which uses a standard. You can get standards that are a few parts per million. You can get some that change 100 parts per million per degree. So that comes into play. Self-heating is a real interesting piece of an RTD. So if you can imagine, you're forcing a current through the resistor. Well, I squared R, there's some finite power being applied to that. And at that finite level, it heats this resistor a little bit. Well, that disturbs your measurement that you're making, actually. So the goal then is to lower this current to a place where this isn't significant self-heating. Then, of course, you're lowering your signal of your millivolt meter has to read, so you've got some loss there. There's an optimal point. And when we get to talking about some of the other calibration, I'll talk about how they do that at the national metrology level for ultimate accuracy. And you also get some thermoelectric effects similar to a thermocouple junction. This will all be copper connections in here. Of course, this was probably a platinum device. But these little connection points, you get little millivolt offsets. You don't have perfectly pure materials. And those little stray thermoelectric effects can also disturb the reading you're trying to make. So what some instruments do to overcome that is they'll alternate the polarity of the current and cancel out that thermoelectric effect. If you're not trying to get real tight accuracies, you can ignore it, but it is there. We also make some very low resistance measurements instruments, and we deal with that often at low level things. Something under 1 ohm is where it becomes really significant, where a lot of RTDs, of course, are operating at higher resistances, so it doesn't become much of an impact. So this is in an RTD circuit. When you're measuring, you'll see 2, 3, and 4 wire circuits. This is a 4-wire circuit. The sense leads are separate from the stimulus leads or the force leads. Of course, if you've got to run that cable any distance in a manufacturing facility, now you want to eliminate some of the conductors. So you'll see a 3-wire circuit. And the 3-wire circuit separates out the these two still, but uses a common ground. So if you've got to run things a long way and you've got a lot of material to run, you can save money. So people will do that. The resistance in this lead starts to become, have more of an effect. But if you've got something out here that's 100 ohms and this is 0.2 of an ohm, maybe you can ignore it. It's going to create some error, but maybe it's less than what you care about. Or if you get your RTD up to a higher resistance, 1,000 ohm RTD, you've made that even less of an issue. And that's what people do then for the next configuration, which is 2-wire. They've basically combined these two into one on both sides, so now you only got 2 wires going out. Any lead resistance here gets into your measurement, but then people use, again, higher resistance RTDs, and that gets you away from having to worry about that lead resistance. However, the higher the resistance you make this out here, the more susceptible you are to interference. So you can start, if these runs are any length, you can start coupling noise in a plant or even in a, some industrial piece of equipment that, maybe it's got some noisy emitters in it, and that starts coupling into your cabling. So these are all things that get in there. Even if you're trying to do a calibration, it's like you can't get a calibration because you can't get the thing to settle down. You might be getting some interference, some electromagnetic interference from somewhere. And this is also the configuration most thermistors, if you recall, 2250 ohm, 2252 ohm thermistors, 10K ohm thermistors are much higher impedance, so they get by with 2-wire pretty effectively.